we were only doing like the first section, and I had like gone through all 45 slides. And I was like, there's no way I'm finna do all this. And I looked at the homework. I was like, oh, pray to God, like
I really
like way more doable now.
I just did like the dynamic presentation. Or no, what was it? Yeah.
All right, so everyone got 100 on the homework, so everyone, I assume, understood it.
Yeah,
For the most part. Is there any?
That was the one section of that 45 slides that I like understood well.
So
it was very reviewed from like the year one stuff.
Okay. Is there any questions you guys had? Was there anything you don't understand while right? Like, did you take any notes about that? Any questions?
Was peak value and average value and effective value, was all that included? Because that was the stuff that I did not have the graph for, that they were giving all their examples from, and so I had no.
That's included. So you need that explained?
Yeah.
Okay. Anything else?
Could you explain the? Yeah, never mind.
All right.
Oh, man. No, you didn't say it.
Okay. All right. So AC is a type of current with changing direction, strength, and voltage over time. What is so fun?
Remember how he did this in test? He'd sit there and laugh the whole time. I don't know why.
Okay.
It's just funny, like watching you teach.
I did this for weeks in the website. What are you talking about? Okay, whatever.
It's just like I'm thinking about school and college and like my professors, and I'm like getting a bar. Like, no.
I have a quick question.
Am I too you? Am I not enough?
No, you're just like, you're a funny person to like have as a teacher.
Real quick.
Like most teachers are like boring.
Hey, could you explain the difference between AC and DC in dumb?
Brother, what?
Okay.
And like when we would use AC and when we would use DC.
AC alternates. AC does not.
Basically. AC, alternating current.
The we will.
The current, meaning this would be the strength, alternates. So it goes from 0 to a positive maximum value, to 0 to a negative maximum value, 0, so on. DC is
direct.
Whatever it is, that's what it is.
So what would be a real world application for
DC is like batteries, and AC
think about
is
motors.
like everything else pretty
Spinning.
much.
Technically, you could use either one for really any application. There's just some things that they're better for. For example, like really low voltage stuff like communication, that's mostly going to be DC.
like Cat 6?
Yeah, that's mostly going to be DC because AC causes interference.
Because it's going up and down. It's changing.
Yes. This will be a section later, but the changing magnitude causes induction.
Yeah, I did not get any of that stuff.
Yeah, so like that's why I only wanted to do the first section for now. But the changing magnitude causes a changing magnetic field, which causes induction, which then causes it's basically a chain reaction because they both cause each other. It's kind of like a really simple explanation, like because I don't want to get super deep into it right now. But AC will cause interference and other things. DC typically doesn't. Well, it doesn't because there's no change. There's no changing voltage. There's no induction in DC.
So you're not saying the voltage is changing up and down rapidly? It's just the frequencies changing up.
No, the frequency stays the same.
I
It's-
mean-
it's the voltage that changes.
Okay, so then how come when you go to how come when you go to when you put a meter on it,
Mhm.
it's not fluttering? Is it
Because
it's going so fast, or
That'll also be covered later, but no, because the meter technically when the meter reads it, it actually converts it to DC, and it gives you the DC equivalent of the AC that's in here. So like RMS value, like if this was, it's like okay, example 120 outlet.
Mhm.
What is the peak value?
yeah, it was 170. That didn't make sense.
Yes, exactly. So 170. Why? Because 120 is the RMS value of 170, root mean square. Meaning, when you take the average of the entire curve, what you get is like it was point. So like this is 0,
Mhm.
this is 1.
Mhm.
When you look at it as a product of sine,
Mhm.
0 to 1, and that's no matter what the voltage is, it's always 0 to 1 because sine is always 0 to 1. So then you can take the root mean square of all of them, and it's going to be 0.707. So if you take 170 and multiply by 0.707, that'll give you 120.
And that's your voltage.
And that is the RMS value,
Mhm.
which is also the DC equivalent. And that's the voltage that's actually usable. So like in AC, you don't have the entire voltage available for use.
Yeah.
This will also be covered later, but it's because of the induction process. Some of that power is being used to generate the rest of the power, basically.
That the that makes
Like-
sense.
It'll be explained more in depth later, but I don't want to get super far ahead.
So do you get all the voltage for like DC?
Yeah, when you measure DC, you just get. That's all. That's just it. No. The key things about AC: direction, changing changing direction and then changing magnitude, and then strength and voltage over time. The frequency can change. There are ways to change the frequency, but in just a regular circuit, the frequency won't change.
Mhm.
The frequency will basically always be 60 hertz. Because generators just generate the electricity at 60 hertz.
In America.
So the horizontal axis, that's
Yes.
Think about
Voltage.
like a circle turned sideways.
Well, it's a time
What?
magnitude, which in this
Just
case
a
is
circle
voltage
turning
because this is
AC.
a sine wave for voltage.
Yeah.
If this was amperage, then it would be amps.
Sine wave's just a circle turned side.
In one complete waveform or cycle, the current changes polarity twice. So this is a cycle. One set up and down,
Mhm. That's a cycle.
cycle. The most common type of AC waveform is going to be a sine wave. That's such a sine wave.
That's what one of my other questions was. What's the difference? There, that is the sawtooth, the rectangular, and
Yeah.
one other one.
We'll get to that in a bit. Technically, this is also a cosine wave. Technically, they look the same.
Oh, you mean like the degrees?
What's going on?
I was just telling him sine wave's just a circle turned sideways.
Oh, yeah. All right, everyone go
I
with
thought
it.
you meant like half the circle. It's like,
No.
I was like, what? Yeah. Yeah, that 170 question, that was like the only question on there that I was like confused about.
You know it was 0.707. No idea.
If you ever forget what the number is, just keep 170 and 120 in your head and do the math on that.
Mm.
All right, so how is it generated? What do you need to generate a sine wave? Specifically AC. What do you need?
current flowing in a conductive material or something.
What generates the current?
Power.
Change in magnetic field.
Magnetism is needed to generate the AC sine wave. There are two principles that form the basis of all electromagnetic occurrences. Count me.
Oh gosh.
Get him water.
Name one.
The way magnetism is generated.
No. Two principles form the basis of all electromagnetic occurrences. Name one.
Changes polarity twice in one cycle.
Nope.
Voltage changes over time.
Nope. It's related to magnetism. Austin, help him out.
I'm sorry, what was the question?
Electric current in a conductor creates magnetic field surrounding the conductor.
Is that in your notes?
Yes.
Good.
And then the other one's something about it has to be running perpendicular to the magnetic field
Well, that's where it generates.
for it to create voltage. If it's the Brian. Hey, Brian.
Do you guys have somewhere to lock a backpack up at?
The game box.
The gay box.
Just
I
talk.
said just put it in the game box.
Okay, 10-4.
Thank you.
Alright. Love you, Brian.
Love you too, bud. Bye.
Bye.
That is getting recorded.
That's recording?
Yes.
Wait, why is it being recorded?
Mark, how does it feel to be on national television?
I'll be happy
Wait,
to
is
make
this
it
for,
through
like-
this class without getting into prison.
Is this like for future lessons?
So you guys can look back at it if you want to review.
Oh, so like other people aren't gonna watch it.
Yeah,
Yeah,
Caleb's gonna watch in three hours.
I probably won't upload this within 3 hours.
You're uploading it to YouTube?
No, I'm just gonna make a Google Drive.
Nice.
VEC University.
Good thing we found out before Ty said the N word.
No, they got recent
Please
videos.
try and save me as much editing time as possible. I don't have to spend additional 8 hours going through this footage to
No, Reese got caught on the horror cam saying
Oh gosh, you should have heard Reese. He said the N word.
Willie
And he
Wigger
get
kill that? No.
and he got caught on the horror cam.
There was a
The horror
poor
cam.
guy right next to it's like what he said.
No, where's the camera?
Yeah, with the camera. Do you know what he said?
I don't know, something.
So man, I don't listen to these or something like that.
I'm not gonna write this whole thing, but
That's fine.
you'll have the voice recording anyway.
I think you know it's supposed to be. Oh, right. You're giving us your notes that we'll copy down, right?
After you show me adequate notes of your own.
Yeah.
Oh.
To give you some context on the amount of effort I've put into this, I have about 400 pages of notes.
For today?
Today.
No.
For
For the class.
Holy shit!
Gosh, so you already wrote like in the past few weeks. You've just been writing notes.
I've done it over like basically since I got hired.
Gosh.
Anytime I was in the field working on specific travel ailments, what I was doing. All right, Aiden, one more time. What are they?
I got it right here. An electric current in a conductor creates a magnetic field surrounds the conductor.
And
Movement between conductor and magnitude field creates voltage.
If
It's perpendicular.
Oh yeah, it's perpendicular.
They don't really think about it. I need something that I
all right, go to figure 1 on page 2.
Figure 1, page 2.
Mm-hmm.
What's that do? Oh, wait, that's for you. Bless you.
How the rest of shoot you.
You have any
For
guns?
legal purposes, no.
So do I need to write it in? What?
No, that's you're gonna put your finalized notes in there, so you have a reference book of everything that you can look back on.
We're not allowed to use this on the test, though, correct?
No.
How many guns do you have, Omar?
Focus on the class.
Do I go to dynamic presentation?
I do want to know.
No, open the textbook,
Excellent.
the e-textbook.
Pearson textbook.
Mm-hmm. Page 2, figure 1.
Conductor moving across a middle.
I wonder if the graph was on this too.
I shouldn't have done
God.
I almost had my master's
Bastards.
and bachelor's.
And what?
Either
Why'd you drop out?
one.
Why didn't you become
All
a
right.
musician?
Everybody there?
C.
Yep.
No, my phone's not working.
All right.
I'm there.
Yeah, I am.
Ooh.
Oh, I could have got that water by this.
You said 2?
Probably have. Yes. Figure 1. Yep. All right. So in that figure, you can see the parts necessary to create current. You have magnets, and you have a moving conductor cutting through the flux created by the magnets.
The end has the magnets.
Yes.
And so that middle brown part is like spinning around.
Yes, that is the conductor that will be spinning.
Stator.
This is basically the simplest version of a generator that you can make.
Your generator. Okay.
A generator and a motor, what's the difference? Functionally. Not functionally, like I don't know how to phrase it. Basically, a generator and a motor are basically the exact same thing, just backwards.
The magnet spin and the wire spins.
When we start learning about motors and how they work, you'll see that they're basically the exact same. They just work in reverse.
As the magnet spin around instead of the.
Yeah, the magnet.
No, it's still the wire spinning.
Uh-huh.
They just take power in and make
Something
magnetic.
make the wires move
instead
through
of
the
taking
field.
something moving and making.
Yeah, instead, so like a generator, something else will move the wires and create the electricity. A motor will take the electricity and move the wires.
Gotcha.
So, at which point of this is it going to create the most voltage?
Probably 1.
A or S.
Oh.
Oh,
No,
wait.
B.
No, those aren't the options. I'm just saying, like, what orientation of that conductor will generate the highest voltage?
Oh.
When it's,
One that's perpendicular?
when it's horizontal, magnets on top, magnets on bottom, facing this way. Guess they're perpendicular.
Agree? Disagree?
Yeah, I agree.
You can tell us we're wrong.
Agree? Disagree?
Agree.
I agree.
Wrong.
Oh, gosh, why? But it's perpendicular.
the conductor is perpendicular, the motion isn't. The motion is what matters.
Oh yeah.
So if this is the flux, when if that's the flux, the magnetic flux. Yep.
Mhm.
Oh, the up and down.
Yeah, yes, the arrows are the magnetic flux
Oh.
between the magnets.
Oh. Okay.
If the conductor shown in that diagram is horizontal, so you would think this is where the max is, but actually, at its current state, the only place this can go is up, straight up. The only place this can go, straight down. Which means these are parallel. So how much voltage is it generating?
None.
Yes, 0. It's not generating any voltage. Now, if the conductor is vertical,
Wait, our conductor is vertical.
yes, it is, but that wasn't my question.
Oh. Well, I thought we were talking about the diagram.
You are talking about.
My fault.
So even though the conductor is vertical, it's motion. Here, the only way it can go is straight to the left. Here, the only way it can go is straight to the right. Completely perpendicular. Perpendicular.
Because
Oh,
to the magnetic field.
Flux.
Gosh. Is the flux just a magnetic force that the flux is?
Basically, yeah. The flux is like the lines of the magnetic field.
The magnetic, okay, got it.
You know, don't.
What does this actually look like? Like, I don't.
What do you mean? What does this actually look like?
They literally got something that be looking like a little circle of wire that's spinning or something. Like, is this legit? What it looks like, or is this just for diagram?
I mean, in a real generator, there's going to be a lot more wires, but yeah, that's like the basic form of it.
Go back. So what are you talking about?
There we go.
All right, what's your question? Right now, we're talking about just the conductors, the copper. The stuff here, 2 and 3, don't worry about that.
How is that different when it's like that?
So,
I gotta check it.
Like, I ain't seeing it.
okay, so in that diagram, so like the blue here is that copper wire, the conductor, right? In that diagram, it's vertical. But because it's vertical, so it's spinning, right? So it's in there and it's spinning like this. The whole point of that conductor is to spin and generate electricity. So because it's spinning, when it's up here, what's it going to do? It's going to spin this way, right? Which means at this point, the movement of that conductor is here and here. So here, think of it this way.
So whenever the conductor is horizontal, that's when you're on your
Oh, I guess I get it.
on your graph, that's at 0. Yeah, right?
Yes. So
So the speed at which that is spinning, that's your frequency, right?
yes. All right. So
Okay, I was confused because I was like thinking about looking at it from this angle, but y'all are kind of looking at it from like that.
all right. So look over here. So the conductor travels in a circle.
Yeah, that makes more sense.
The movement that the conductor is going at any given moment, the direction in which it's moving, you only look at it at the very end of it, because that's the part that cuts across the magnetic field. So the point at which the direction in which it's moving is going to be perpendicular to the way it's oriented. So if it's this way, its movement is over here. It's always going to be, because it's going in a circle, right? And the magnetic lines, they don't change. Magnetic lines are always going to be like this. Yeah. So the amount of voltage generated is decided by the direction of the movement. So here, nothing. Here, a little bit. Here, a lot. Here, max.
So there's a positive and negative side to that.
Yes.
What is that thing called?
The generator.
The polarity?
The copper wire. What is that called?
The conductor.
Yeah. Yeah. That makes sense.
Would it be easier to explain that, like, if you use magnet as the conductor instead?
How would the magnet be a conductor?
Well, it's not, but like it'd be easier to conceptualize with the magnetic fields, I guess.
We're using magnets.
Huh?
We're using magnets.
North south.
That's a magnet.
It's not that. It's not that simple. If you were to add two magnets and start spinning them, though, like it's a complex. Like,
Let me see what I did with my Kindle.
With your what?
My Kindle. Oh, there it is.
Kindle fire.
All right, we good here?
Yeah.
Yeah. Like I thought you were looking at it that way, and you're supposed to be looking at it that way. You know what I'm saying?
No, you're looking at it from the front.
Yeah. That's the way he's saying he didn't know we were looking. He was like,
Yeah.
Okay.
And I was like,
I don't know why
like,
they drew it like 3D like that. I mean,
Yeah.
I guess to hammer home the fact that it's a generator, but it would have made a lot more sense if they just drew it like
Yeah.
looking directly at it.
Maybe you should go tell them what's up.
They made a lot of mistakes in the like typos and like just legitimate mistakes. At one point, they added a table of wire thicknesses like KC mil, and they were off by like a factor of 1,000. Because like 12 gauge is like 6 KC mil or something, and they put 6,000 KC mil because I guess they meant 6,000 C mils, and then still put KC mil instead. Okay, so is it generating the same level of voltage all the way around?
No.
no.
Okay. What are the 3 factors that affect the amount of voltage developed?
Frequency, period, and over.
No, those are the parts of a AC sine wave. What are the factors that affect the amount of voltage developed?
Now. The
Frequency has nothing to do with it. Yeah. Stop saying frequency.
what are the 3 factors that affect the amount of voltage? The speed at which the conductor is spinning.
Yes.
That's the frequency.
Technically fine.
I'd say like the amplitude would probably be one.
And then the magnitude.
Magnitude.
That's an effect. I'm asking for the causes.
The amplitude.
The field itself.
What field?
The straight magnitude.
What about it?
How long right there.
Yes. And the third?
The thickness of the conductor.
Close.
The material.
No.
The
Thickness.
length.
Yes. So, 3 factors: conductor speed, how fast it's moving through the magnetic flux. Technically, yes and no on the frequency, because increasing the frequency would increase the speed, but also keeping the same frequency and just making a bigger generator also makes it move faster. Because that's physics. It's so.
Oh yeah, it's technically moving faster.
Yeah. So it's covering a much larger distance
To the outside.
in the same exact amount of time.
To the outside.
So it's moving faster. So yes, you can just speed it up, and that would increase it. But we don't do that. All generators work off of 3600 hertz. Or megahertz. 3600. 3600 hertz. How do you decide what voltage a generator produces?
Just guess.
The RMS. The RMS. No.
No. What are the physical characteristics of a generator that decide what voltage it produces?
Doesn't that have something to do with the neutrals?
Magnets and conductors and the cord.
Oh, duh.
The trifecta.
For any given generator, one of these will change, and that changes what voltage is produced.
So could you? Yeah, you could have two generators where the conductor speed and the magnet strength are the same, but the conductor length is different.
Mhm.
Right. Now, I have a question.
Mm-hmm.
Do you have two different transformers? Wait, not transformers. Generators. That they both produce the same amount of voltage, but the factors are different in each.
I mean, you could mix and match these to create two different generators that make the same. It's like you could increase this and decrease this, and then just cancel out. Yeah. Gotcha.
Is that what the difference between brands of generators are?
There's not a whole lot of physical discrepancy between generators of specific voltage, because typically they're like one
Most efficient way to.
Yeah, there's like one or maybe two like ways that are most efficient, or like one way is the most efficient, but it's a little bit more fragile. So in some instances you use that, in other instances there's one that's less efficient, but it's hardy, so you use that one.
Gotcha.
But in general, like there's really just going to be one best way to do it.
Gotcha.
The rate at which the conductors cut the magnetic field depends on two things: the speed of the generator in RPM and the angle that the conductor cuts across the magnetic lines. Which of these determines voltage and why?
Wait, what was the first one?
The speed.
It would be the second one.
The speed of the generator in RPM
Be the
and the angle that the conductor cuts across the magnetic lines. Which one?
The angle.
Which one determines the voltage of the generator? Not the voltage of the sine wave at any given point. The voltage of the generator.
Yes, it's kind of both.
An RPM.
Yeah,
RPM, both.
It's gotta be RPM because the RPM will change based on what you have plugged into, but the angle will stay the same.
Thinking with both? It's RPM. So the question is asking how much voltage the generator produces. So that means
Not where it's at.
let's say
Oh, you mean not at any given point, like average?
like the actual output of the generator.
Oh,
So let's say the generator produces 200 volts. If we want to increase that and make it 250, we would increase the RPM. We wouldn't actually, because pretty much every generator works off of 3600. Really, I guess technically it just has to be multiples of 60, but I'm pretty sure most of them go off 3600. And then the angle at which it cuts across the magnetic field, that just tells you where you are on this line specifically. But it doesn't tell you the overall output of the generator.
Because the angle stayed the same.
I just didn't know you're talking about overall output as basically
Yeah.
like the point on the
The angle is constantly changing.
Yeah.
Yeah, never mind. I know what you meant by angle.
Didn't see that
Angle
coming
of the
up.
conductor.
Figure 2, page 2.
Figure 2, page 2.
Mm-hmm.
The one with the motion.
I like to keep talking to myself.
You're not grounded?
I'm very staticky today.
Why does your dumb question? Why does your truck shock you sometimes? Get out and you'll touch the door.
Because you're brushing against your seat, depending on the material you're wearing and the material of your seat, you're going to exchange ions.
Your tires are insulated.
So you're gonna be either ion deficient or ionized. So when you touch something, you either give off a bunch of ions at once or you take in a bunch of ions at once, and that's what shocks you. All right, everyone see that?
Is this getting into Fleming's left-hand rule?
What?
I said, is this getting into Fleming's left-hand rule?
They never mention it, I don't think, but I think it's in my notes, like my own. It's been a while since I made these notes, so
It's been a while. There's a box right there.
all right. The arrows represent motion, meaning the motion of the conductor at any given point. So basically these arrows that I drew over here. So here, the motion of the conductor, and these are the flex lines, the motion of the conductor is parallel to the flex lines. So how much voltage is being produced here? Here, perpendicular to the flex lines. How much voltage is being produced here?
Depends
The
on
max.
The max.
Yeah.
Now here is the variable
Is that the lag?
that symbol is called phi, the Greek letter phi.
Mhm.
And it represents this angle right here. Anytime you see that symbol, phi, talking about an angle. So,
Or fraternity.
the angle phi
Well,
is going to be the angle between the lines of flux and the current motion of the conductor. The magnitude of the voltage produced by this is going to be proportional to the sine of the angle of said interaction.
okay, yeah.
Any questions?
No.
Okay, good. Explain that, Ty. Explain what I just said.
is proportional to the angle that. I guess self-explanatory.
That's great. It's self-explanatory. Come explain it.
You just said that.
All right, come on. Come here. There you go.
Yeah, you took calculus.
I did.
Don't say yes if the answer is no.
Well, I think
Come
I
up,
understand.
come up here.
All it.
Up here.
You literally just said that this angle is proportional to this angle. Right?
Nope. I'll read it again.
Okay.
The magnitude of the voltage produced by this interaction will be proportional to the sine of the angle of that interaction.
The magnitude, which is where you're at on the graph,
Yes.
proportional to the angle at that any given point. So, like, you got that.
Mm-hmm.
It's going to be proportional to that. You have it here. It's proportional there.
Proportional to what specifically?
The time axis.
Magnitude of the voltage produced by that interaction will be proportional to the sine of the angle of that interaction.
Oh, the sine of that angle. Yeah.
Okay. That means the voltage here is the sine of this angle.
Sine of 90. Okay.
The voltage here is the sine of whatever that angle. And so on and so forth. Now, does that mean that sine of that angle is going to equal 150 volts?
No,
What? So that means sine is going to equal what?
the proportion to the max.
It's going to equal the proportion. So
Max.
a number between 0 and 1. At 0, sine of 0 is 0.
Oh, yeah. 0 to 1.
Sine of 1, or sine of 1, 1, and then everything in between.
You said sine of 0 is 0?
The sine of 0 degrees is 0. Sorry, the sine of 0 degrees is 0. The sine of 90 degrees is 1.
Gosh.
The sine of 180 degrees
Is
is 0.
Yeah.
Everyone on the same page?
Mhm.
Okay. So, I think I showed all of you this already. Some of you were more receptive to it than others. In the field.
Right, you should.
Good gosh. Not this specifically, but this also, this exact same thing applies to. This exact same thing applies to conduit bending.
Yes.
I know who you're talking
The
about.
cosecant of your angle bend multiplied by the hypotenuse is the length of your bend.
You know what Aiden's words were today? He was like, it's nice when we can, like, not been pipe for a few days. You come back and just raw dog something without measuring it, and it'd be right.
Then be like, I still got it.
And then send me a picture of a dog shit ass night
I wasn't done.
in the electrical room.
Looks great now. I'll have you know.
Should have seen my holes I drilled going to the electrical group.
That was some ugly stuff right there.
So here, phi is going to be 30 degrees. And the way this works is, bust out the calculator, give me sine of 30.
2.
Ain't that,
Or no,
I used to know this.
it's just like 0.4.
Hang on. Sine of 30?
You don't want the arcsine this time. Yeah.
Negative 0.988?
What?
0.5.
Wait, cosine of 30?
Radians
No,
or
sine.
Sine?
0.5.
Yeah, I got 0.5.
What calculator?
Yeah, switch
degrees.
calculators.
Hold up. Sine of 30. Yeah, 0.5. Okay.
You can also take the arcsine, which is
You multiply.
the inverse.
Uh-huh.
And that's just going to give you That'll give you 2. Because the inverse, you know what inverses are.
Mhm.
Fraction
1 divided by.
like that. It's swapped her up.
The inverse of a number is whatever number you got to multiply by to get 1.
Oh yeah.
So the inverse of 0.5 is 2.
Gotcha.
And arcsine is the inverse of sine.
Oh.
So the reason you double whatever this is, whatever this is, to get whatever this is because it has the exact same trigonometric relationship as that phi does in angle and voltage calculation.
So you're saying at 30 degrees, the voltage would be half the max.
Yes.
Gotcha.
Do 45
Degrees?
Mm-hmm.
I used to know.
Bro, if God made trigonometry like not
0.707.
it would be so good.
Does that sound familiar to you?
Yes.
0.707?
Yeah. Oh, so 45 degrees then is
So-
your
Like
your
RMS.
RS.
Mm-hmm. What's the inverse of that?
Oh gosh.
That would be
You can either do arcsine of 45 or you can just do 1 divided by 0.707.
undefined.
Isn't it 0. 0.
Is it arcsine or is it
1.41?
Undefined.
Sure, not cosine.
is arcsine the inverse of sine? I
I don't have arcsine on my calculator.
It's saying undefined.
Hang on, cosine of. Hang on, let me try something. It's gotta be
1.7.
cosine.
Arcsine of H
Yeah,
is 4.49.
it's gotta be the
it is
arcsine.
arcsine.
Yeah.
Did you use the a sine key or did you put the sine -1 key
Sine to the negative first power.
of 0.45 or 45?
Yes,
And
and
it
it told
gave you
me
undefined?
yes.
I just did sine of 45. It gave me. What's 707?
You can just put 1 divided by sine 45.
Oh yeah, that's your arcsine too.
1.414 2135
Yeah.
Well, anyway,
What's the answer?
the 1 divided by 707, 1.41.
Uh.
Does that look familiar?
Yeah, sure.
That's your multiplier in 45.
Oh,
And you can do the same thing for all of them 10, 22.5, and 60.
oh, that's what you want. 5 1
Mm-hmm.
Gotcha.
So like when you're doing your offset, this is your multiplier for a 45-degree offset.
All right.
We'll go over this more in the pipe bending section.
Let's talk about it.
Your
Parallel
bending
adjustment.
section.
Parallel adjustment.
What?
Parallel adjustment.
Use your words.
Yeah.
Formulate a sentence.
You're talking to the dummy here.
Huh?
You're talking to the dummy.
Voltage
Hey man, got that.
voltage at 0 degrees is 0. And the sine of 0 degrees is 0. Voltage is maxed at 90 degrees. And the sine of 90 is 1. What happens when you get to the other side?
Comes negative.
Yep. So that means the sine of 270 is
Negative
-1.
1.
So
I
but
don't know why my brain was thinking like 270 was over here.
whenever it's negative, that doesn't mean it's pulling the power back.
no, it's just a charge.
Like a battery.
So the potential difference, the potential power, is the same. It's just coming from a different direction, basically.
Is that why
Boom.
when you're hooked up with battery, or like let's say you're gonna run in DC, you'd have a positive and a negative wire.
Mm-hmm.
In AC, you've got your hot,
Mhm.
your positive and negative are inside that wire.
Mhm.
Okay.
Your
Stuff's packed through the.
neutral's technically a hot.
Yeah.
It's just half of like a face to
It's
face
just the extra voltage.
No, the
center tap.
it's the neutral is technically still hot. It just has no potential. It has no potential.
Yeah, it carries a
because it's
difference.
grounded.
Yeah.
So it has no potential difference between itself and the ground.
Mm.
But it still has current. All right. Figure 3, page 4.
It's 4. Got your decks out this week. Wow, not found now. You got me kidding.
It's not too big of a deal because I'm gonna draw it anyway. Pretty sure they messed up that drawing because they labeled something as either the max or the min, and like I looked at it a million times and for the life of me, I don't think they're right. Yeah, because at number 2, they have that labeled conductors cutting directly across field EMF maximum.
You want this one?
No. Figure 2, page. Oh, so figure 3, page 4. Sorry.
What you doing?
Figure 2.
That's the
Figure 3, page 4. It's on page 4. It's a sine wave with like the corresponding points
Brother,
on a generator.
That's what.
Well, what he said didn't say that on
This?
here.
No, it looks like this.
Alright. There. Yes.
You can click on it, make it bigger. At number 2, they have that labeled conductors cutting directly across field EMF maximum. Does that look right to you?
No.
No, because it's at 0.
Yeah, so it's
It also says the same thing on 3.
yeah, so like it yeah, I mean yeah, that too.
It should
They
be
just got
EMF
1 and 2
minimum,
mixed
right?
up.
Yeah.
Should be EMF minimum.
Yeah. Yeah, so I guess that's
Wait,
what
but number 1 says EMF minimum.
yeah, so the this diagram is just wrong. They got 1 and 2 mixed up.
So
Well, actually,
one-
no. One is right. 1 is the minimum.
Mhm.
1 is the minimum because it like the motion.
Yeah.
The conductor itself
It's
is
parallel.
perpendicular, but its motion is completely parallel with it right there. So that's 0.
Yeah.
At number 2, it's the exact same thing as number 1. They labeled it wrong.
It's also at this minimum.
Yes. And you can see because it corresponds to the 0 on the AC sine wave.
How would you be the maximum then when it's below the X?
What's your question?
How is 3 the max if it's below?
Negative whatever voltage is not less than positive whatever voltage. They're the exact same.
Just
Plus 120 and minus 120 are the same amount of power.
When you say it's just different polarity,
Yes.
So then, how is
Like-
2 the same as 1 if 2 is horizontal?
They're both in the same position. They're both at 0.
That's the same.
it's parallel to the magnetic flux on both of them.
Like A and C.
Oh, I was looking at A. Oh. Duh. Okay.
Alright, we're on the same page now?
Yes.
Okay.
Okay, so B and D are the same thing.
Yeah.
Yes.
Gotcha.
Alright, so we've got 0 to 180. And we've got 180
360.
to 360. This entire thing is what?
A phase.
No.
Oh wait, sorry. Yes.
Cycle.
A phase is in 1 second.
No.
Phase.
What's this?
That's a phase. My fault.
Phase.
No.
So
Aiden?
period.
No.
Frequency.
No.
Hertz.
It's an alteration.
What?
Alteration.
Oh, I didn't know we were supposed to use them. Okay.
So the one entire sine wave is 1 cycle.
I thought it was alternation.
Alteration.
It is.
One alteration.
That makes more sense, actually. I wrote all this by hand. You write 400 pages of
That's
that.
why they call it the alternator.
All right. So one alternation, second alternation together, they make one cycle. Now, if you look at I want to go over this right now. No, I don't. Yeah. All right. Why does the polarity reverse at 180?
It becomes negative or positive. Or it becomes
Bro, what even is polarity? Like,
Because
I don't
it's-
even-
Positive or negative?
This is at the magnetic field.
Because it's at the magnetic field.
because it's at the
It's at the opposing field.
because there's like
Yeah,
a
it's at the
north and
opposing
south
field.
pole.
Yeah.
No. I mean, technically, but no. I mean, it is there, but that's not why it reverses.
Because the pool keeps it going through.
Because one side.
I didn't remember you're talking to a college dropout here.
I'm gonna-
Really?
Aren't we all?
How far did you make it?
A year.
You made it for one. See, technically, I made it a year. I did a
I went
crap
back.
ton of dual enrollment.
I went back 2 times, and I was like, "Why did I do this?"
Well, I did go through California, so excuse me.
Where did you go to college at?
BSU, UMC.
I was talking.
Huh?
Hampton, Sydney.
Where?
Hampton, Sydney.
In Australia.
No, it's in Virginia. Were you both about to ask Australia?
Yeah. Two brain cells think alike.
At one end, it makes positive voltage.
Mhm.
At the other end, it makes negative voltage.
Mhm.
What's the difference?
The magnets are opposing each other.
Look at the drawing that I put on the fucking board.
One is up there, one's down there. One's north, one's south. One's negative, one's positive.
The direction of flux.
The direction it's going.
No, the direction of the conductor.
The direction it's spinning.
The orientation.
The colors.
6, 7.
Up here, it's moving this way.
Yes.
Down here,
You're
moving the opposite direction.
Yes.
Now,
I'm not even remember.
could you not start it spinning the other way? It'll work.
That's what they do in Australia.
Fix right now.
Is that why like some motors are like one way and some of them are the other way and stuff?
What do you mean?
Like
mean
how
like
they can
rotation?
reverse?
Yeah.
Kinda. I mean, you can just swap any two legs. And
Yeah, but that's what I'm saying. When you swap them, no, because you're not doing that.
I mean, this is a generator,
Yeah.
which I mean, like we'll get into motors later, but basically, it has to do with the interaction with the magnetic field. Yeah.
So, if you were to swap the rotation of the generator, would that have any effect on the voltage?
No.
About to hear a bunch of Australian jokes now.
The voltage along any point of the sine wave can be determined with
E equals E max times E pi sine of E pi. Or pi. Wait,
Okay, what is E?
phi. Yeah, phi.
Did you
That's what
just ask me what E is?
Hang on. E.
I'm about to send you back to first here.
Just said it. Hang on. The volt. No.
Oh, come on.
There you go.
Hey. The peak value.
What are we calculating?
I don't think I ever got one of these.
Yes, you did.
You did.
What are you calculating?
Energy.
Brother! What kind?
Volts.
Start calling it Tyler.
You call it your
That's fine.
Dude, he hates when he gets called Tyler or Tyrone or like anything else. Like, oh,
I had two brothers that grew up from me down the road from me. One was named, they were both black. One was named Tyler, the other was Tyrone.
Tyrone.
Volts. Oh,
Voltage.
voltage, okay. That's the max.
Max.
Volts. Voltage.
Thank you.
The side of the angle of wherever you are on the graph.
Times the sin of the fraternity.
sine of phi. Sine of phi.
So what this means in effect is you have your sine wave, you have your maximum voltage, whatever that is.
Whoa. Luminaire.
Your voltage was two.
Let's just find
No,
out.
we're talking about 120 volts. That would be 170, right?
I wrote
Yeah.
77.
I know. So, but 277 would be the 45. Or is this some wacko voltage difference?
This is just like finding where you're at. Like
277.
So this is where. So when you multiply it, the other one.
What do you mean wacko voltage? You use 277 every day.
I know. That's what I'm saying. If we were to use 120, it would say you would have written 170.
The max voltage doesn't matter. I could have written 7,355,000.
So you're just doing this as an example.
1.1 gigawatts.
It was legit 277 volts. 277 would be at 45 degrees, right? Get what you say?
You mean like when you test it?
Yeah.
And it says 277? Yes.
Okay.
Nominal.
Yes and no. Like as far as you're concerned, it's 277 and you're working with 277.
Okay.
But like on the math end, like behind the scenes, yes, 277 would be at the 45.
Okay.
But like when you're doing your math for like in the field, no.
You don't do that.
No.
Okay.
So
because that voltage is getting lost, so you're not having to deal with
it's not really lost, it's just being used for something else.
Gotcha.
So the point of this wasn't to confuse on whatever
Yeah,
fuck
yeah.
you're talking about. The point was just that you can use this to find the voltage value at any point along the sine wave. Just by figuring out where it is on the sine wave. So if it's at, we'll say,
30 degrees.
no, we'll say 176. You would do voltage equals
277.
max voltage 277 times the sine 176, and that will give you the voltage in that
Wait, so-
spot.
Is 176 your degree or is that your voltage?
That's 176 is degree.
Okay.
It's your
Yeah, 176 means 277 voltage potential.
All right, we'll take a break real quick so I can help out Jalen on something.
Hey, roughly how much are we? Yeah. Is that actually sure.
We're halfway down.
Yeah, that's what I want to
Okay.
do.
It's not activated.
We might be here, or I might be here.
Yeah, you got down.
Did you get here earlier?
Yeah.
Which means I used to keep my shit braided.
Oh, really? So
That's why I know. That's why I wear a skull cap.
the in the same, like right after the picture they gave you the instructions, there's a code. Take that code and put it right there.
Is it letter? Oh, okay, yeah, I know what that is. Let me see.
What? No
Or-
way. He's teaching that in
Or like
Rudo?
20, just full.
Did you immediately start playing Clash of Clans?
No.
No.
Clash Royale.
Whatever it's called.
Yeah.
That's gay.
What the hell?
Yeah, bitch. Hello.
But yeah, I gotta cut the thing on the inside of my hard hat so it feel like my head.
Yeah.
Mm.
All right, but
So what I do now? So will it let me flip on it now? Oh god.
yeah, that's your class.
Okay.
Yeah.
Okay.
Mhm. All right, so everybody clear on this part?
That was the break.
I said I just need to. I mean, how long do you want to be here?
Dude.
I got video games to play. I don't know about you.
I got a work to ponder.
All right. Finally, in 1.1.
Clash Royale. So
Alright, from now on, I see you playing Clash Royale and taking your fun.
Or you're not.
Yes, sir, Mr. Professor. I don't play Clash Royale, so I don't have to worry about that.
I feel like I probably have to like ban something way too specific for you.
For who, me?
Yeah.
Oh.
Alright. Important terms. Period. Wavelength. Peak value.
Peak value.
Average value. Effective value. And frequency. Aiden, what's frequency?
What's what?
Frequency.
How often a cycle is completed per second?
Yes. Now, frequency is one of the words that your book gives you purple clickable text in the textbook
Mhm.
that opens up a flashcard, which by the way you can make your own custom flashcards. When you're in the e-textbook, highlight whatever you want to highlight, right click on it, and you can make a flashcard out of it. So anything that they took the time to highlight in purple, click on it and make sure you remember their definition. And their definition is the number of cycles an alternating electric current, sound wave, or vibrating object undergoes per second. So. What's frequency measured in?
Hertz.
What's the notation for hertz?
HZ.
Any of those capital?
Capital
H.
H.
H is not
H.
And Z's?
uncapitalized lowercase.
So 1 hertz is 1 cycle per second.
Oh.
Alright, go to figure 4 on page 5.
Trying to generate
I love generating.
What does figure 4 look like?
Let's figure
A squiggly piece of spaghetti.
much.
Bless you.
Everybody found it?
Yeah.
Alright, what's the frequency?
Hold up.
So
8 hertz.
2 hertz.
Ty?
My iPad is. Page 4.
Page 5. Figure 4.
What is the frequency?
Mm-hmm.
Actually, it's 10.
Oh yeah, 10.
10.
Oh, it's gonna have to wait.
What is the period of a waveform?
What is the how long it takes for one cycle to be completed?
Yes. What's the period of figure 4?
Half of a second.
It takes half a second to complete one cycle.
1 second. Like
All right.
like one.
Depends on how depends on hertz.
Yeah, so of that specific example, what is the period?
0.1,
0.5.
0.05.
Stop yelling out numbers.
It's 0.1. It's got it.
Why?
There's a formula. It's 1 divided by.
It said it.
Okay. The period is how long it takes to complete one cycle. What's a cycle?
360 degrees of 1.
Okay. How many cycles are in that figure?
5.
And what is the time frame of those 5 cycles?
5.
So what is the period of one of those?
0.1.
Oh, yeah. All right.
You said that after you yelled like 10 other things first.
I said 0.1 first.
No, you didn't. Period is the inverse of the frequency. So period is denoted with a T. So T equals 1 over F. What the inverse of it?
Question: when we're going back to study for our year 2 test, will us going through these notes that you've given us, will that be sufficient?
You won't be taking that same test again. That was just to completely skip first year. So what's going to happen, the way this is going to work is there's going to be like a test for each module. And so after we finish module 1, AC sine forms,
That's it. We'll take a test after that.
you take a test for that.
We will
And
have
then-
to take a test.
And then you get NCR certified for that module.
Praise God, because I did not want to take another 15 years worth of material test. That was awful.
As far as I
I
know,
had to
there's no
study.
final.
Okay.
So how long is it going to take?
How long is what going to take?
This entire
This class,
A
Yeah.
year.
6:30.
144 hours, give or take. Probably give,
But
because you keep interrupting me with dumb questions.
and that's just year 2. Okay.
Yes, we are on you.
What is a wavelength?
Distance of a period.
The distance traveled by a waveform during one period. A period is a unit of time, not a distance. But it is the distance traveled by a waveform.
Someone's got to make a period journals.
I've been thinking.
It's notated
Lambda.
Up that upside down.
Lambda.
What is it called? Lambda?
Lambda.
T times C.
And it's basically like an upside down Y.
They told me it was like upside down B.
Yeah.
Hey.
Duh. Mine spelled it lamp. Duh. You've heard it.
Well, the physics, electromagnetic radiation travels at the speed of light. So the wavelength of electrical waveforms is the product of the speed of light and the period. Which means. Lambda
1.86.
or wavelength equals t, meaning what?
Time.
Fine.
No. Time period.
Period. Times c. Speed of light.
C is the speed of light.
Yep.
Okay. So that's a given.
Yeah, that's just the formula. Or you can do lambda. Hey, dropping there. Equals
C divided by half.
speed of light divided by frequency. Everybody understand that?
So if we C divided by F equals T times C.
Yes.
It's like your pot.
Gotcha. Sorry, my algebra brain.
Your what, brain?
Algebra. I was trying to I'll figure out T equal F, but that does not work like T equal whatever F is.
All right. Peak value.
That's the max, right?
Now this is peak.
Max value of what?
Voltage.
Just voltage?
Everything. Voltage, hertz. No. Voltage, amplitude.
Also known as
Magnitude.
Current.
Current.
I.
You.
Was that the chair or were you?
That was him.
That was him.
does peak voltage apply to the positive or the negative?
Both.
Yes.
Both. Please say we're right.
Yeah. So the peak to peak meaning from here to here is going to be 2 times whatever the peak.
From the top from peak to peak, it's 2 times the peak.
Yes.
Because they're both the same. Just because it's negative doesn't mean like from here. So if this was 120, from here to here is 240.
Inside of you.
Degrees. Okay. Gotcha.
No, voltage. If the peak value for a voltage was 120,
Uh-huh.
that means it's 120 in both. This is negative 120, but not really. It's still 120.
Mm-hmm.
I mean, it is negative. The voltage difference between these two, 240. 240. How do you calculate average value?
It's 0.637. No, that was the example. That's what I had a question. It said 0.637 times the peak value. I didn't know where they got 0.637 from.
The average value is the average of all values in a sine wave for one alteration. So this is one alteration. The average value is all of these added up and then divided by the amount you added up, so 180. And that number is 0.637. Nice. What angle corresponds to that?
Or 6.
Read it right.
Ain't that 60?
That's not 180.
Calculator. There you go.
What is sine of 0.63?
$57.3.
39.
89.9. So 90.
Why did you multiply by 90?
You said what's the
Why did you want to 1 divided by the sine?
39.568.
Huh?
It's
I did that.
It's arcsine.
I don't have arcsine.
Click
sine,
the
sine
second
minus
button.
1. Sine to the negative 1. You should have like an alternate.
Yeah, click the second button. Are you in basic mode?
If you hit the second number, it'll give you alternates for. Oh. And you sine minus 1.
I should have left my scientific calculator in the perfect form. Hey, get back here. Huh?
Right. Running away from me.
Whiteboard, more like whiteboard. I feel like I'm back at college.
Root mean square.
Root beers.
What'd you say?
root beer?
What's that also called?
RS.
Mm-hmm. Root mean square.
Or.
The effective value.
Oh wait.
No, wait.
You just said it.
Awesome session. You guys are like, yeah, totally. The thing that I just thought of on my own. Nobody said it. All right. When you use your meter to test voltage on anything, AC, what it's giving you is the root mean square or effective value.
2,000 amp view.
It is the measure of energy transfer that is equivalent to a direct current or voltage. So AC and DC currents can be compared based on the heat they produce because heat is only affected by current amplitude and not direction.
Mm-hmm.
What does that mean?
Do you say that again one more time?
AC and DC currents can be compared based on the heat they produce because heat is only affected by current amplitude and not direction.
The more current there is, the hotter it will get.
Same amount of energy.
DC isn't rotating.
Yeah.
So the AC gets hotter.
There's no angle.
So AC changes directions.
Huh?
Goes to positive. It goes to negative.
Oh,
Positive. It goes to negative. It changes direction.
with a circle.
DC just stays the same.
Uh-huh.
The way you compare them is by the amount of heat they produce. You can't. There's no other way to compare AC.
Oh, there's no way to put a difference. That's the heat.
No, you can tell the difference, but there's no way to compare relative strength of them.
Gotcha.
Because they're just functionally too different, and the way you compare them is the amount of heat they generate. Because AC current is a sine wave with changing values, which include 0, meaning there's no heat. Here, and here. 0. And here and here would be maximum heat. The instantaneous value of AC must be higher at times to have the same heat production. Meaning,
He's taking the circle, flattening it out.
what's instant? What is it? What does it mean by instantaneous?
Like a-
Single
I just
instant in time.
So like any individual point on the wave would be an instantaneous value. So all those words summed up means since the values are changing, sometimes the instantaneous value is higher in order for the average to be the same. That's all that means. And that's why you use effective values to compare them, because the effective value is going to be the average value of comparable heat. The most common method, because we already said 0.707 is 45 degrees. So the most common method is just taking whatever the value is at 45 degrees. And doing that. So the book's definition for root mean square. The multiplication of the square root of the mean value by the squared function of the instantaneous values throughout the period. The RMS value of an AC voltage or current is the effective value of the voltage or current. So, effective value means how much heat it can produce, how much work it can do. So, once again, the 120, 170. The actual value of this 170, the useful value that we use is 120. Okay, phase relationships. I don't let your parents watch my videos.
Why?
I don't want to have to do that much editing.
Why my parents?
Here's the motion.
Not going to land. Vault.
Not much left.
Let's see this guy.
But Ryan tried to pop my back yesterday. He's so big. He's a fucking big bear hug.
Oh, I knew that one time that I was like, this one's good.
Brian is obsessed with trying to let him crack my back.
He's just trying to crack.
So that's me, pop it. I think there's a squeaky floor in them. Yeah, right here. Made some new chairs.
And edit.
All right. With AC, phase is used in one of two ways. Name one. Aiden.
I don't know. Can I guess?
Sinusoidal and non-sinusoidal.
I guess that.
No.
Okay. Is that like single phase, double phase,
Double
No.
phase.
or triple phase?
3 phase.
Wait, what
Big
was the
phase.
question? What are the uses?
With AC, phase is used in one of two ways.
Sinusoidal and non-sinusoidal.
Nope.
2 uses.
The location of a point on a voltage or current wave.
Oh.
See, I think this is about where I zonked out last night going through it.
Well, don't wait until the last night to do it.
Oh, I was sick the whole week. I had
You
to
look
take
like
my
dog.
grandma to the beach.
In relation to the start of the wave. Did you take your grandma to the beach?
She was visiting from Minnesota.
Did she fly down here? I guess so. Or did she fly to Atlanta?
Yeah, you gotta walk
Yeah,
around down.
the hospital.
Okay.
I like from
Any guesses to the second one?
Just a cycle.
The frequency.
Location of a point on the wave in
like randomly like
wave.
Relation to a corresponding point on the same wave.
Oh,
You're gonna have to explain that.
Okay.
I need to see it to believe it. No, you don't.
You got two options. First option, from some point on the wave to the start of the wave. Second option, from some point on the wave to another point on the wave.
Okay.
The comparison is usually done at the 0 or max value points. So it's usually going to be done here, 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 here. One may be ahead, meaning it's phase leading, or behind, meaning it's phase lagging. How do you know which one is leading and which one is lagging?
Lead is at the max, and lag would be below the max.
Anybody else?
90 degrees.
Well, I have the graph right here. I don't know how to explain it.
Anybody else?
what was the question?
What time would you like to change your
Writing
answer?
it down.
Well, I have the graph
90
here. I
degrees
just don't know
LC.
how to explain it. I guess that'll understand.
What was the question?
Here, draw two different graphs, and I'll tell you which one's which. Okay, that is not the graph they gave. But my guess is blue is lag, and red is lead.
Yeah.
Actually, no.
Phase-
I should
phase
have
lag.
drawn it like this. Hang on.
Phase lag is 90 degrees behind.
Sure. Alright. Which one leads? Which one lags?
Blue leads, red lags at that point.
Agree? Disagree?
Like a ball.
Don't know.
Oh, red. Yeah, red leads.
That's not what he said. He said blue leads.
Huh?
He said blue leads. Red lags. You disagree?
I feel like red should lag.
I feel like it's like in relation.
Okay, this is the graph they gave us. Where like one graph is under, it's not.
That's
I guess with
those
this,
are,
I would
those are the
say
same. Those aren't lagging or leading.
I would say
that's
blue
something
leads.
else. Blue leads. Blue leads, red leads.
Blue leads. We'll go with that since it's
How do you know blue leads?
because it starts the graph.
higher. It starts at 90 degrees, and red starts at
0.
It starts at 90 degrees.
Well,
90 degrees is here.
it starts at 1.
That's 180.
That's 180.
It depends on the.
Oh. Yeah, true. So it starts at 50.
So why does blue lead?
Because it's 90 degrees.
Because it reaches 90 degrees first. Or it's farther along in its cycle at 90 degrees than the other
No, these are happening at the same time. Well, one is going to be voltage and one is going to be current. They happen at the same time.
Well, yeah, but in each of those waves cycles, like the actual what's that called? Period or whatever.
This is why you should read the textbook instead of these stupid slides.
Of course, stupid slides.
But no, I thought you should read the textbook.
That's what you said.
Would you like to bet?
You can't. What is the self-learning guide? Is that the reading? Self-learning guide was the
Read and do the self-guided learning for section 1.
self-guided learning is the dynamic present.
Right. And read the textbook.
Oh, I didn't know the textbook.
So this line represents time.
Really?
So disregard the start and follow this line. The first one you come across leads.
That's what I said. I said blue was the lead because it reaches 90 degrees first. Like
They reach 90
like coming back down.
They reach 90 degrees at the same
Like
time.
coming back.
This is still at 90 degrees.
Yeah, but it's like
It crosses
farther
it
along.
crosses
Yeah, that's
the
what I
zero
meant.
first.
That's
But
what
that's
I
not
meant.
what you said.
That's what I meant.
But it's not what you said. I can't
Alright.
read your mind. You have to use your words.
I meant like it reaches whatever.
How much does it lead by?
90 degrees.
So that means this has
A quarter.
blue has a phase lead of 90 degrees, and red has a phase lag of 90 degrees.
God.
This thing always cuts out right as I reach for it. Every single time. It's like it knows.
Don't touch me.
This is fun. You can draw these as a vector.
Victor.
Vector. Oh yeah.
Saw your hint of 8.
Why does it look like this?
Because
90 degrees.
Why is the phase angle 90?
it's 90 degrees out of.
So they're 90 degrees out of sync. So this is what their vector is going to be 90 degrees. What is this comparing?
Current and voltage.
Right. The think back to the generator.
Oh.
No. So the flux. This is the motion of a conductor. This is the motion of a conductor. So imagine if this was instead of current and voltage, think of this as two phases of voltage.
Okay.
So that would mean when one phase of the voltage is this way, meaning its conductor is at the bottom, and it's at peak bottom, moving this way. That means the other conductor is at 0. It's over here, moving this way, and that's this vector angle here is literally the comparison of the motion of the of where it is on that circle.
Well, could that technically be like of 2 different phases of wire when you're pulling like 3 phase?
Yeah.
So when they say like phases are out of sync, those are not 90 degrees.
Yeah, so like 3-phase poles,
180 degrees.
they're it's 120 degrees out. There's 360 total degrees, each one 120 off. So the equivalent of this, one generator started a cycle at 90 degrees. So this one, and then one's angle started at 0. So one started at max, one started at min. What has to be the same for both? Here, there.
The angle?
What has to be the same for both
The frequency.
sine waves? It has to be the same. Why?
Or else they wouldn't be the same every time they cross the.
So this angle, if they were a different frequency, this would constantly change.
Mm-hmm.
Can I erase this?
Yeah. ¿Cuántos más minutos
One more page.
missed the wave? I think if my parents saw this video, they'd be more disappointed in me than with you.
Phase angle diagrams. Vector diagrams are used to each AC phases. That's basically what I just drew. What is a vector? Not related. Not to this. Like what is it? What is actual
It's a vector?
Yes.
It is a point. No, it is a line with a direction.
Sort of. A quantity that has magnitude and direction.
Oh yeah, it's got like the angle and the direction.
Yeah, so you need a value, a magnitude, and you need a direction that value would
Is
move.
that like or the angle of that
Line.
The length, the angle of the vector is its direction, and the length would be the magnitude. Is speed a vector?
No, because a magnitude.
Okay.
Yeah, when you like that's like the difference between like the speed of something and the velocity of something.
Yeah.
The only thing I physics.
So I already showed you the vector diagram for that. So now we have the one you were looking at. What would the vector for these look like?
It would be the same vector, but like direction, but the magnitude.
Same page, everybody? Okay. So these are in phase.
In phase, okay? Is that no bueno?
That just means there's no lag or lead. They're in phase.
There's no
Okay. They're the same phase, same frequency. The only thing different between them is when they're in phase, they actually, and you can see it on the vector too. When they're in phase, they actually add together. So now their total vector, their final total voltage is this entire thing.
Case where you pull that down?
Sure there is. I can't really think of any. Now for that other one, I drew the one that was at an angle.
Yeah, that's every single wire pull. That's two equal.
Well, no, that's like cancel out.
So it would be angle, right?
Assuming they're both exactly the same, which these are, yes. The final vector angle of these would be at a 45.
Same magnitude.
Yeah. And I think that's later in the chapter we actually do this math.
Gotcha.
It looks a lot more daunting than it really is. It's super. We good here?
Sí, señor. Y papi chulo. No mames.
I have to write this word 1,000 times in these notes.
Preston's gonna.
Non-sinusoidal waveform.
Oh, sinusoidal. All right, got that one.
I may have just written it wrong.
Sinusoidal. No, I wrote it wrong.
Okay.
Sinusoidal.
Why is a sine wave the basic form waveform for AC?
That's its natural tendency.
Alternating.
How does a generator move?
In a circle.
Circular motion.
It's just a circle turning up.
Okay.
Produced by a rotary generator, so output is proportional to angle of rotation. Because they result from circular motion, sine waves can be analyzed in angular measure. Just basically everything I've been talking about up until now. Angular measure is expressed in degrees, 0 to 360, or radians, 0 to 2 pi. What's radian?
That was something dumb in calculus that I never
Measure
explained once. Oh, that's 2 pi. No.
2 pi. 2. I'm about to say.
No. I wasn't about to say that. It's I wrote it down right now.
There's like zero.
While I draw.
2 pi times radians.
Yeah, that's what I just said. Radians go from 0 to 2 pi.
Yeah.
What is a radian?
360 degrees. No. Radian.
Angular measure.
What you said?
Expressed
So-
as a
Circumference of a circle gives you 2 pi radians. A radian is an angle formed, or it's expressed in 2 pi. So if you had a full 360, it'd be 2 pi. Now, a radian is an angle formed at the center of a circle by an opposite arc of the circle equal in length to the radius. So this is let's say that is about your radius. That means that's a radian.
angular measure.
Good? You basically just need to know the definition. Absolutely none of our math is going to use radians. Technically, you could do it with radians, but why would you?
If you're dumb.
For electronic applications, other wave shapes are important, which you were asking about this. So, any wave shape that is not a sine wave is called a non-sinusoidal waveform.
Use of soil.
There's a couple of different versions. There's the it's just square. Then like, then I think it was like rectangular.
Yeah. Sawtooth. Yeah. Jigger Jagger, yeah. Bee-boo. I played all the way.
So why do they look like this?
The question was.
So
Because they're not
these
circular.
are produced by a generator which moves in a circle. So it has a smooth circular motion creating a sine wave.
Probably like
Created
this, then.
artificially by digital devices.
Mm-hmm.
So, for example, a variable phase drive
Oh yeah.
that controls the motor, it will, if it's a really cheap, shitty one, it'll look like that. Yes. No. Yes. No. That's it. And it, if they're a little bit better, basically, like the more expensive and better the drive is, the more steps it'll have. So it'll, gotcha. Step its way up and then back down, and same thing. And it's trying to mimic the wave, but it's digital. It can't. No matter how many iterations you give, no matter how many steps you give, it will never give the infinite curve of a circle. It will always be some attempt at a copy. Will always be steps.
But he doesn't give up. But he doesn't give up.
Comparison to sine waves. In all cases, the cycle is between the 2 points of the same amplitude. So no matter what kind of wave, the sawtooth, whatever, this is still a cycle.
Yeah.
In all cases, peak amplitude, whatever the highest point is, measured from 0. Caveat to that is peak to peak amplitude is better for measuring sinusoidal waveforms. Or sorry, is better for measuring non-sinusoidal waveforms.
Because it's more accurate.
Why?
Action.
What if it looks like this? What if the positive is only like 10, but the negative is 120? So non-sinusoidal waveforms can be uneven, which means peak-to-peak measurements give you a more accurate description of the actual power they perform. Because this would be 130.
Mm-hmm.
If you measured it just using this, you would think it was 10, or I guess technically you would think it was 20.
Mm-hmm.
You double it. If you measured it just using this, you would think it was 240.
Mm-hmm.
The RMS factor, does that apply to these?
No.
Mm-hmm.
Nope. Why?
It's constantly changing.
Specifically, why is it waveforms?
Well, because it's a continuous. There's no root. It's a smooth circle.
It's like one value pretty much along the line. It doesn't like change very much.
RMS? What's the definition of RMS?
Root mean squared.
How much useful heat / energy.
Right, but like the mathematical definition of RMS.
Square root. I know.
It's the average of all the points, right?
Oh yeah, yeah.
Specifically, the average of all the points
if you had
of the
that,
sine value.
it's just only 1 point.
Sine can only be used on a sine wave. You can't use sine on this, so you can't get an RMS value. Yeah.
Oh man, anyone would like
about like the
fuck
20 steps to
love? Like,
forgot to think.
so I don't have any notes right now.
It's fine. I don't really want you guys taking notes during class. Just go back once I post the video, watch the notes, watch the video, make